Hey everyone, my name's Leonard Gunther. I'm a student doing a TAE and this is my assessment 6 of 6 for the delivery program, delivery cluster. Hey everyone, how are we all tonight?
Good, thanks.
Good. How many have we got? 1, 2, 3, 4, 5, 6. There's a couple still on their way. Well, they said they'd be here, so I will just go ahead and I'll come in when they do. So how is everybody? Have everyone had a good Christmas?
Yep.
Thank you all for helping me out again. I'm just going to share my screen. Can we see that? Can everybody see that?
Yeah, sure.
Okay, that's good.
Yeah.
Okay, I don't know how to get everybody in there. So I can see Aidan, I can see Nadine, I can see James, Kathy, Lucy,
Matthew's there.
Matthew. Here we go.
Matt Mitchell.
Yeah, I'm trying to get everybody that I can see them all. And Matt. Okay, guys, so we'll just go ahead and the other will probably join us when they can, hopefully. Anyway, so we're looking at our screen that I've shared with you. So we're going to talk tonight about final sub-circuit design. Now, if you remember the first lesson we had, we spoke about the maximum demand, and we looked at a plan, and we counted up all the power points and all of the load that we had on that circuit, and we calculated our maximum demand. So we're going to do something similar. We're going to use the same plan, and we're going to design our final sub-circuits. So when we talk about final sub-circuits, we look at our meter box, and you'll look when you go to your meter box. Normally, you've got fuses or circuit breakers. So they're our final sub-circuits. So you've got lights, you've got power points, power circuits, you've got your stove, you've got your air conditioning. They're our final sub-circuits. So what we're going to do tonight is we're going to look at our plan that we've already looked at. We're going to work out what we're going to put on each of those circuits, what size cable we're going to use, and how we're going to protect that with our circuit breaker or a fuse or an RCD. So we'll do the same sort of thing. We'll look at wiring rules, and we'll look at there's no calculations in this one, and we'll just look at how we're going to design that and where we're going to put our power points on each circuit. Okay, so that's our outcome. That's what we want to achieve tonight, to be able to pick up a plan, look at it, and work out exactly what we're going to do when we go into wire a house. Okay, everybody on the same page? Everyone understand?
Yep.
Yeah, we've got everybody on board now, I think, which is good.
Yes, Len.
8, that's beautiful. Okay, so we'll just go to the next slide. Next one. We've got housekeeping. So have we all got a well-lit ergonomic work area? Yeah? Is it all well lit?
Yeah.
All good.
Have you assessed your area for any hazards such as trip hazards? We don't want to fall over and break our leg, do we, Kathy?
No, we don't. Thanks, Lenny.
Kathy broke her leg yesterday. She's not very happy. Are you familiar with your emergency exit location? You know how to get out in a hurry? You know where your scooter is?
Yeah, I know where my scooter is.
Okay, and I don't know if you had a chance to print off the answer sheet that we had. It doesn't matter, we can get by without it. But if at the end we've got a feedback sheet, if you could print that up and fill it out and send it back to me, that'd be fantastic. And I've also emailed you a presentation pack, which has basically got copies of these slide rules, the rules of the wiring rules. So if you can't read it on the screen, you can access it there and have a look, just in case. Okay. All right, we'll move on. As we did in our last lesson, we looked at this picture here where we've got a typical house, and you've got your consumer mains, as you can see, going across your service there going across, and your consumer mains go from your point of attachment to your meter box. That's what we worked out last time. So what we're going to work out tonight is from our meter box to the rest of the house. Does that make sense to everybody?
Yep.
Yeah. Everyone's good with that? Matt? Yeah.
Yeah.
Yep.
Huey down there, you good with that?
Yeah, mate.
Yeah.
Gotcha.
And what about Yvette, Scotty? Josh is good, I'm sure. He's an electrician. He should know all this. And the girls are all good? Good stuff. Okay, so we'll go on to the next picture here. And as you can see with this picture, might look like a lot of lines to those laymen here, but this is basically your meter box where your fuses are outside on the house. So you can see here, these things here, they represent like switches. So they look like they look like switches. So they're basically circuit breakers. And so you got a main switch and then like your circuit breakers, and these red, green, and black, that's what we call our final sub-circuits. So you can see one there goes to this hot water system here. You've got one there that says power circuit, and you've got one here that says lighting circuit. That's what we're going to look at, working out those cable sizes and how many points we're going to have on these circuits. Is everyone good with that?
Yep.
Yep. So we'll move along. So we know what our final sub-circuits are now. These are our protection devices. Okay, and that's what we done last time, consumer mains. So we'll go back and we'll have a look at our plan that we had last time. Okay, so this is our example plan. And you can see here, as I said, these little triangles, they represent power points. And these little spots here with the dotted lines, they represent our light fittings. And you'll also see other things in here, like there's one here, that's a smoke detector. So our smoke detectors in our houses now, we have to wire them in to our light circuits, so they're permanently connected to electricity, and they'll go on the lighting circuit. So you can see that, those little dotted lines, that's just the wiring for the switches. Go back to our switches on the wall. So you can imagine in your house, you got your switch on the wall. Well, that's what that cable there represents, where it's going across to that light fitting. So where it's switched from. So for instance, at your front door, you might have 3 switches at one plate. One might be for your hallway. There's one for your porch light and another switch for the other lights outside. So you can understand how that wiring is. Okay, we all on board with that, girls and guys?
Yep.
Yeah, okay. So as I said, we've got our power points. We've got our lighting points. In the kitchen, we'll obviously have an oven or a stove. The hot water here is a gas hot water, so it's got a power point there, so it'll ignite by itself. So it's permanently connected into a power point, so it ignites the same as you would with the gas cooktop that would plug into a power point as well. What else do we have in here? In the bathroom, we have something here over the shower. That's an exhaust fan. So generally we have exhaust fans in our bathrooms. So we count those as a lighting point as well. So you can see over here, I've got load written up there. So you've got lighting points. So I've counted all the lights up here, and there's a total of 27 light fittings. And then we've got 2 smoke detectors and 2 exhaust fans. So if we add all those together, we've got a total of 31. Does that make sense?
Yep.
Now, if you look at our power points, socket outlets, or what we call power points, the layman, as we call it as electrician socket outlets, each one of those little triangles there counts as 1. So a double point, that counts as two points. Okay? Because you can plug 2 different things in there instead of just 1. You have single points and you have double points. So each of those little triangles represents 1 socket outlet. So if we counted all of those points up, all those little triangles that we see, there's 21 double outlets and there's 8 single outlets. So if we got the 21, multiply that by 2 because they count as 2, that's 42 plus 8, that's a total of 50 little triangles there. So this becomes more apparent later when we move on to the next few slides, and you'll understand why we have to count them as 2. Okay, is everybody on board with all that?
Yes, that's great. Thank you.
So we can see all our little triangles, all our little lighting points. I know it's a little bit hard to see. Can you all see that plan clearly?
Yeah.
So we're all good with that. Okay then.
Yes.
Okay, so as we did with our last lesson, we had AS 3000 wiring rules. So we have to follow those wiring rules again when we come to this calculations or this exercise. So we have a thing called current capacity. When we spoke about our consumer mains in the last lesson, we had to work out the current capacity. So we worked out the total load of the whole house, and we had to work out the current capacity of the cable coming into the house from the point of attachment. We have to do the same sort of thing, but for a circuit. Okay. So generally, every conductor has a current capacity in accordance with AS 3000 or 3008 and tells us what size cable we need to run. So in layman's terms, we just have to worry about, in a domestic situation, we have thermal insulation, you know, the pink bats up in the roof. So we have to be aware of that, because that can affect the heat of the cable and the heat factor on it. So therefore that can change our current capacity of our cable, because the more current you put through a cable, the hotter it gets. So we don't want to go over that heat rating of the cable. So we have to be aware of the fiberglass insulation. So we assume that every house has thermal insulation, whether it has it or not, because it could go in at any time afterwards. As you know, the Labor government a long time ago with Peter Garrett, they had a program to put thermal insulation to all these houses free of charge at the government's expense to make them more efficient. And what happened? A lot of people got hurt, went up in the roofs, heat exposure, electrocution, they got electrocuted, houses caught on fire because cables overheated, and it was a total disaster. So now, as far as AS 3000 and the wiring rules and the rules that electricians have to work by, we have to assume that there is or will be thermal insulation in a house, so we cater for that from the start. Everyone good with that?
Yep.
Any questions?
Did they not implement a government program to rip it all out?
Well, I
Kind
don't
of
know
like
whether
the same
they,
as asbestos, you know what I mean? Like,
well, I'm not sure on that, Aidan. Maybe one day it will, but at this stage we're not sure. It's hard to say, but at this stage we just have to assume that there will be thermal insulation regardless. So, so I'll just go on to the next slide now. And as you can see here, Kathy just had to get up next to the door. Here's a table, table 10. And it says here that we've got these cables here, and it says here that we've got conductor size in this lane here, this column. And you'll see that I've highlighted 1.5 and 2.5. So when we look at cable sizes for power circuits, the minimum size cable for a power circuit is 2.5 millimeter squared. So we have to use that as a minimum. So generally when we wire a house, we wire our houses with 2.5 millimeter squared for our power circuits. And when we come to light circuits, the minimum size there is 1 millimeter squared, but it's not a real good choice when it comes to durability and because it's single solid core and it can break, where we go to 1.5 generally nowadays, and because that's stranded and it's stronger, and we get a better current capacity out of that as well. So you can see there, partially surrounded by thermal insulation, unenclosed, so it's not in conduit or anything like that. So that's what that means, unenclosed. So just clip to the side of the timber with thermal insulation partly around it. That's partially surrounded like we normally do in a general installation. You'll look down that column and can see that the 1.5 millimeter squared for lighting will carry 14 amps. So we can load that up to 14 amps. And the 2.5, it says 20, so we can have 20 amps on that. So we all good with that, people?
Yes, Gary?
Yep.
Any
Yeah.
questions there? Because I know it's a little bit confusing. If you look at these other columns here, completely surrounded, that means that that cable would have insulation completely right around it, as you can see in the picture. So that reduces that current carrying capacity yet again. Okay, so this is a problem that they had when they put insulation in the roofs of houses. There might have been insulation in part of it and they put more insulation on top of it. That's dropped that current carrying capacity down. That circuit's been drawing so much power and it's overheated, caught on fire. And that's the issue that we have with when they say that's an electrical fault. It's more of an overload of the current of the cable and the current carrying capacity of the cable. So everyone good with that?
Yep.
Okay. So if I go to the next table, here, this is the last rules one that we need to worry about. And this is the guidance on the loading of points per final subcircuit. So this is just a guide. Generally, what you would do is you can work out the load on what you're going to have on that circuit, and then you can pick how much you're going to put on it. So I generally like to follow the preferred loading. Okay, so if we look here and we've got a cross-sectional area of cable, so millimeters squared, and the green one is lighting circuits, as I've highlighted there, 1.5. So this is our circuit protection. In this column here, you can see there it's A for amps, and there's all numbers going down that column. And when we get to the highlighted one there at 10, so what I want to put in there, and what I prefer, and what every other electrician would prefer, is you run that on a 10 amp circuit breaker, which is fairly common. You don't want to go and buy a 13 amp one because you probably wouldn't buy one anyway. And if you did, it'll cost you an arm and a leg to get it. So the standard there is a 10 amp. And what that's telling us there, lighting points, you've got to allow half an amp per lighting point. So therefore, on that lighting circuit for 10 amps, you can have 20 lighting points on that circuit. Does that make sense?
Yep.
We've got a dinosaur.
Yes, we do.
So therefore we can have a total of preferred number of points is 20 lighting points. Now you might say, well, LEDs, they tell us that they only draw 6 watts, so they don't draw much power and all that. You can have a lot more. Well, yes, you can. But this is just a guide. So as this guide, we'll stick to the guide. And by doing it this way, we're not going to have any problems later on. If somebody wants to come in and extend onto that circuit and put more lights on that circuit in that house, they're not going to have an issue with it, with that size cable. Okay, so what we've seen there is this 10 amps and 0.5 equals 20 points on a circuit, on one circuit. Everyone's good with that? We'll go down here to
Yep.
socket outlets. Yes,
Can I ask a question?
certainly can.
Seems to be quite important in the size of the cables. Is there a huge price differential? Because sometimes they just have corners.
When it comes to if you have a look across here for the when you look at single out phase multi for socket outlets, see it's got NP there.
Yeah.
So you're not allowed to use less than 2.5 for a power circuit, as I said previously. So you have to use that size cable as a minimum.
Oh, of course. Yeah.
Okay. So with lighting, and it's not much difference between 1 millimeter squared and 1.5 millimeter squared.
Right.
At the realistically, for what it's worth, the amount of problems that you can have with 1 mil, it's better to have the 1.5 these days. So That's a very good question. So the price does come into things when it comes to wiring houses. It does make a big issue if depending on the quality of stuff that you finish the house off with. And a few of the electricians that I know and that are here tonight would agree with me that some companies do use cheap quality fit-off gear. But when it comes to the cable size, generally this is like the ruling. So when it says here's socket outlets, we're using 2.5 millimeter square cable and we've got a 20 amp circuit breaker. So that's telling us there, if we look across here, with permanent air conditioning, we can allocate 1 amp for each little triangle. So for each socket outlet. So therefore, we can have a total of 20 points on the circuit, on a power circuit. So everyone's good with that?
Yep.
So we all understand that? Any questions? It's pretty straightforward. It's not rocket science. And you can see here in the blue, I've got range. So on a 20 amp, on a 2.5 circuit, a 20 amp circuit breaker, we're allowed 8,000 watts for a load for a range. They generally would go a bigger cable than that for a range. For an oven, we would run a 2.5 circuit. And if we had a separate cooktop, we'd run another cooktop circuit, a minimum of 2.5, depending whether it's an induction or just a plain electric ceramic cooktop. Induction cooktops, we have to start looking, when we look at our permanently connecteds like our stoves, air conditioning, etc., that's when we have to work out using Ohm's law and work out how many amps, how many watts divided by the voltage to work out how many amps that circuit's going to draw. Okay. But at this stage, we're allowing, it's only a standard oven, so we're allowed to run a 2.5 circuit for the oven there. Anyone got any questions there? We all good?
All good.
All good. So now we come to the fun part. We've gone through what they tell us what we need to do with our rules and regulations. As I'm sure we've got a plumber in here, he's got rules and regulations he has to abide by. We've got a landscaper that he's got his rules and regulations. Everyone's got their regulations. So we have to abide by, so it makes everybody safe. So just to recap, our lighting circuits, we're going to wire them in 1.5 millimeter square cable, and we're going to protect them with a 10 amp circuit breaker or RCD. Okay, because every circuit now in Australia and New Zealand, domestic circuit has to be protected with an RCD or a safety switch, which is the layman's term. Safety switch is layman's term for an RCD, residual current device. So our plug sockets, which are our power points, our oven, our air conditioning circuits, they're going to be wired in 2.5 millimeter square cable, and they'll be protected with a 20 amp circuit breaker. Okay. So we've determined here from our table 9, which this one was here, table 9, that we can have a maximum of 20 points on both our light and our power or socket outlet circuits. So, looking at our plan, you can see I've highlighted a few things there. So as you can see, I've got these green ones here. I've worked out that we've got a total of 50 socket outlets. So if we divided 50 by 3, we'd have 3 17s is 51. So we've got to look at having at least 3 circuits there with around 16, 17, 18, very similar. We don't want to go 10 on one, 20 on the other, and 10 on the other circuit. We want to balance them out. So we balance our load, okay, throughout the whole house. So you can see here, for instance, with this green circuit, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Did I count that one? 13, 14, 15, 16, 17. On this yellow circuit, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you can see how that's got, say, 17, that's got, say, 16, so 18, sorry. And you notice here also that I've got the laundry on one circuit, on the green one, and I've got the kitchen separate to the laundry. Anybody got an idea why I would do that?
Where your biggest loads are going to be.
Exactly. So you don't want to have in the laundry the dryer going, which draws power. So anything that heats draws power. You don't want to have the dryer going in the morning. Mum's got the dryer trying to get the kids' clothes dry for sports day or whatever. She forgot to wash and get dry the day before. And in the kitchen, she's got the kettle on, she's got the toaster going. Then all of a sudden, you're going to overload that circuit because you've got all those heating devices going at once. So what we want to do is make sure that we separate those and balance our loads accordingly. And then you can see here where these red dots, that's our lighting circuit. So because we've got 31 lighting points, we can have 20 on each circuit. We're going to split that in half. So you can see here I've highlighted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the other one will have 15 on it. And including our smoke detectors. They're included as a light point, remember. How's that? All good?
Yep.
So we can understand what we've done there. So what generally I do, on the way to a job, I'll have a job card and we'll work out, we're going to take 2.5 twin and earth, we're going to take 1.5 twin and earth, we're going to take all our cable we need for that job to wire the job. And on the way to the job, I'm going to say to the apprentice, here's the plan. Have a look at the plan and work out what you're going to put on each circuit. So what they'll do is they'll count them all up and then they'll work out how they're going to balance that over the circuit. So I'll give that job to the apprentice on the way to the job. So he's not sitting there on his phone going like this and playing games or whatever, or texting his mate or whatever on the way to work, or his girlfriend or whatever. He's actually doing something instead of sitting there or going to sleep like most of them do. So I keep them busy. And that's their job on the way to the job. So when we get to the job, he knows exactly what he's going to do. And what he generally does, he'll either highlight them or have a multicolored pen, like four color pen or something like that. And you'll circle all his circuits along the way.
Question, Len.
Yes.
Mate, are you also running something bigger than 2.5 for the oven and cooktop?
As I say here, we've got it's a upright dual oven, so it's only a 20 amp oven with a gas cooktop. So we're only running the one circuit, 20 amp for that. Now that depends. Each job's different, depending on the size of the oven. It may require a larger circuit, but you have to look at the specifications for that appliance. Okay, so generally you would have that information from the builder to say we're going to install this cooktop or this oven or this air conditioning or whatever hot water system, whether it's solar, boosted solar, gas, whatever. So you get all that information with your job card before you get to the job, so you know exactly what you're going to run in that house. Generally, sometimes you might turn up on the job and you'll liaise with the owner, and you'll walk through it with the owner, and the owner will tell you what they want, and they'll give you the specifications of their appliances or whatever and what they want in their kitchen. It depends on the job. Some big builders, you've got all the information. Smaller builders, they might tell you to talk to the owner ask them what they want. Okay, so just got to play it by ear when you get to each job, but generally if you've got all the information, you can go straight in and start wiring that house by using our rules and using our rule of thumb there with the number of points per circuit and our cable sizes. So here we go. We've got this now worked out how we're going to show you how we're going to do it. This is the finished product before we start wiring it. So the apprentice has sat there, he's worked out his total number of points. He's got 3 power circuits, P1, P2, P3. And it says there on P1, he's got 6 double power points, 4 single outlets, which totals 16 points. So that's under his 20 points. Okay, so P2, he's got 8 double power points. 1, 2, 3, 4, 5, 6, 7, 8. P3, he's got 7 double power points and 4 single power points, which is a total of 18 points. So you can see how he's balanced that. All those points over 3 circuits. Now you can change that, and you don't actually have to do it that way. You might think, well, I might make the kitchen over 2 circuits and change that around. So we're not loading everything on 1 circuit in the kitchen. It's totally up to you how you design it, but you just want to make sure that you stick to the rule and the suggested 1 amp per point. Okay, so you can see there also there with the lighting, we've got 2 lighting circuits, L1 and L2. So on L1, he's got 14 light fittings and 2 exhaust fans, which is a total of 16 points. And L2 is 13 lights, so they've got 2 smoke detectors, it's a total of 15 points. And then he's got the oven with the gas cooktop, 20 amps, and ducted air conditioning, 20 amps. Okay. Any questions there, guys?
Nope.
So you can see how we do that and how we work out what exactly is going to go on the circuit. Yeah. Okay, all good. So this is just another rule. That's just saying that nowadays we have to have RCDs or safety switches on all domestic installations and residential installations. That's so to save people's lives. That's on everything, including our power, our ovens, cooktops, air conditioning, everything. Okay. So everybody understands that. That's actually Australia only. I thought it was New Zealand as well. Sorry about that. I gave you a bit of a bit misleading. It is only in Australia. It's not in New Zealand. Because you can see up here AS, NZS, Australia, New Zealand, because they cover we cover their rules as well. So if we go to the next slide here, you'll see number of final sub-circuits per circuit. We've worked it out there, and this is just a bit of a table I've made up where it says L1 is 16 points, 1.5 millimeter square cable. The cable's got a current capacity of 14 amps. We're going to protect it with a 10 amps RCD MCB. So we don't want this here over this here. We want to have a smaller number here than we do here, or equal or lower. We don't want to have a 14 amp current carrying capacity and put a 20 amp circuit breaker on there, because if we do that, it'll try and draw 20 amps if it can. And if it can, it'll heat up the cable and melt the cable. And that's what most electrical fires are. People use the wrong size fuse wire. And what happens is, on a light circuit, they put a 20 amp fuse wire in, and then it overloads and starts to melt the cable. Okay, so do we all understand what I've done there? It's just a bit of a table just to see what you, so you can see it. Do we have any questions, guys? Yes, Scott.
No, mate.
Yes, Scott.
Sorry, mate.
You got a question?
So might sound stupid. So going off, your little your table there, the electric oven gas cooktop combo and the duct, obviously the ducted aircon, they're running off separate. They've
Circuits.
got their own wire going from. Is
That's
that right?
right. That's correct. They're just
Separate
on their own
circuit.
separate circuit.
Sorry, it's been
That's
a long day.
correct. Yep. No, that's fine. No, it's understandable. No, that's it. That's all it is on that circuit. It's just the wall oven. With the air conditioning, the only thing on that circuit is the air conditioning. Everybody else good?
Yep.
Okay. So here we go. Did anybody happen to print this up to be able to do this? Scotty has. Anybody else? Maddie has.
Yeah.
Yeah. Okay, so if you haven't, it doesn't matter. Huey's got it too. All right. Well, all those who have printed that up for themselves, you can work on that quietly. And just with the other guys who haven't got it there, we've got a house here. All right. And you guys who are doing that quietly, don't look at the screen. Okay. So this is our little house we've got here. We've got a student exercise. So considering that a double outlet is equal to 2 points, we have a total of 29 socket outlets. So we counted up our little triangles here. You would see what we've got there. So it says, for one, balance the load over 2 circuits. Try to keep the kitchen separate from the laundry. Okay. So by doing that, we'll probably look at this as our laundry here, all you guys. So we look at probably going from the meter box to this point here. Then we go from that point there back to this point. And then we go across to there. So that's 1, 2, 3, 4, 5, 6, 7, 8. Sorry, my mistake. 2, 4, 6, 8, 10, 11, 12, 13, 14, 15. So you can see what we've done there. We've just gone basically one half of the house and kept our laundry on that as well. So that's easy to wire, easy to work out. So when the other one, we go from the meter box here, we go over to here, and we'll pick up our kitchen here and over here. So you'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. Okay, all good? All good. Okay, so what we should have, people, is this. Who got that?
Aced it, mate.
I'm not finished.
Oh, well, hurry up, Scotty. I need you to hurry up.
Hang on, just 2 more minutes, just 30 seconds.
Well, while you're working that out, is anybody okay with the design method? How we design that?
Yeah. Yeah.
Okay, so we're all good with that. So you can understand how we're going to implement this implement it on the job and how we're going to go about it on the job, yeah?
Mm-hmm.
Okay, so I think we've reached the outcomes that we want to achieve here. Everybody understands how we work out these circuits, and we understand how we work on our cable sizes and our circuit protection. If I can show you here, here's a little load center there. Okay, so that's our circuit protection. That's what you probably see in your meter box. Okay, so everybody understands what we've got there. Yeah. Okay, so all our circuit protection. I do have some cable sizes here, but they might be a bit hard to see. There is different types of cable. These are the types of cable that we use. This is an orange.
You got 30
circular.
seconds, Len.
Yeah, I know. I'm watching it, mate. Okay, so, well, so going forward, you can see how we're going to put these new skills into practice on a new house. And I encourage you all to practice what you're doing, and make sure that you can, if you get a chance, pick up some plans,